June 6, 1944, 4:30 hours, Omaha Beach, Normandy. The horizon was a ragged line of smoke and distant tracer, the sea a slate bowl hammered by wind and shellfire. Men crouched behind hedgerows and broken obstacles. A Sherman's turret whispered as a loader rammed a 75mm M3 shell into the breach. The air tasted of cordite and diesel. Orders snapped over radios that crackled like old lightning across the headland. U.S. Navy deck log, June 6, 1944. At 20 degrees left of the ruined pier, Company B of the 741st Tank Battalion readied to back an infantry sweep. They expected to face a battery of PaK-40s and a pair of Panzer IVs reported in village ruins to the east. Doctrine from Armoured School taught crews to engage the glacis plate, point, aim, and fire. Training ranges at Camp Roberts and Fort Knox had drilled against static silhouettes, not shifting iron in mud. The mismatch between textbook ballistics and combat geometry would be costly. The first exchange produced confusion more than carnage. American rounds that should have penetrated simply glanced or detonated harmlessly in churned earth. German crews clambered out to jury-rig barrels and drive away. Privates whispered that shells hit over the engine deck, despite the rangefinder reading 800 yards and the gunner's reticle centered firm. Commanders logged baffled entries. Weapon performance within expected parameters. Enemy effect not mitigated. 741st Tank Battalion after action, June 1944. Blame was cast first on weather and powder. Fog reduces muzzle velocity. Rain ruined optics. But the pattern repeated in Sicily, Salerno, and beneath the Bocage. Ballistics from clean ranges did not match ballistics in smoke and hedgerows. When a hulking panzer presented an acute slope, the line-of-sight target was a lie. The forward plate's angle multiplied deflection chances. A shot on target often winked away, leaving crews furious and bewildered. The brutal geometry taught itself quickly. A strike at the rear hull, the engine deck seam, or the lower side, delivered on a slight trailing bearing, a deliberate fraction behind the perceived position, encountered thinner plating or critical components. Immobilization, not superficial charring, achieved decisive tactical value. A smoking engine meant the tank would sit and burn or be abandoned. The practice became known in crew slang as aiming behind, a counterintuitive move that traded apparent accuracy for mechanical advantage. Field Report, 3rd Armored Division, July 1944, Composite. This was not a neat doctrinal update from Washington. It came from patchwork innovation. A master sergeant scrawled offset degrees on ammunition boxes and passed them along. Ordnance technicians at Aberdeen Proving Ground ran angled plate trials and recorded new ballistic tables. A site engineer at Detroit Arsenal modified elevation drums to show recommended trailing offsets at specific ranges. Credit aggregated like rivets in a hull. Range crews, test engineers, factory fitters, turret gunners, and the civilians who stamped parts on assembly lines. Aberdeen Proving Ground Test Notes, 1944. At first it felt like guesswork. Gunners schooled to aim on the front had to rewire instinct. Loaders timed rounds with an internal count. Commanders delayed the command by a heartbeat. Gunners learned to place the reticle slightly forward of the enemy's present nose so the shell would arrive where the machine would be a fraction later. Radios began sending terse corrections. At 800 yards lateral 5 to 10 km per hour, apply 0.5 mm trailing offset. Field scribes compiled these notes and sent them to Battalion HQ. 4th Infantry Radio Log, July 1944. The human cost was immediate and blunt. Early adopters paid with mangled turrets and burned pride. The method required nerve and precise timing under fire. But outcomes shifted. After-action notes from units using trailing offsets reported doubled immobilizations and higher capture rates. Prisoners were found in tanks with pierced engine blocks and intact turrets, a telltale sign of rear impact damage. Where crews clung to old doctrine, enemy armor often escaped with slashed radiators and furious crews. 4th Infantry After-Action Summary, August 1944. Psychology changed as mechanics did. Watching a German tank heave and stop, smoke spurting from a pierced block, had a leveling effect on infantry morale. Fear sharpened into tactical hope. Infantry commanders started timing assaults to coincide with a tank's trailing shot, trusting that an immobilized vehicle would pin enemy fire and create a widening seam. On the other side, captured German unit reports recorded bafflement and growing despair at being disabled where they expected to be invulnerable. Captured German Unit Memo, August 1944, Composite. Practice hardened into procedure by dusk. Crews rehearsed offsets in moonlight. Mechanics filed sight beds. Armorers adjusted bore alignments. Radio logs of ranges and offset corrections were collected and forwarded to ordnance. The language of gunnery shifted. Aim behind, predict movement, trust arc and time. Small innovations, a washer here, a mill mark there, multiplied across units. The frontier between survival and annihilation shrank to fractions of a degree on a sight's dial. Yet crucial questions remained. What precise interplay of speed, range, and angle yielded the best disablements? How would this scale to aircraft gunners chasing fighters or to anti-aircraft batteries firing at low, fast attack profiles? What calibration changes would be required at scale in Detroit and Rock Island supply lines? Engineers and technicians would be drawn in. Men who translated scraps of field wisdom into revised manuals, production adjustments, and site calibrations. Ordnance Lab Correspondence, 1944. The next phase would pull in ordnance manuals, factory floor reports, and names of the technicians whose small fixes multiplied into strategic advantage. Engineers at Detroit Arsenal and Ordnance Labs would publish corrected ballistic tables. Site makers would change drum graduations. Crews would practice lead calculations until the motion of enemy machines became a predictable arc. One engagement, in particular, would force a full technical reckoning and produce data that transformed everything. Section 2 will reveal the engineers, the factory changes, and the decisive battle. Soon, the secret factor was simple and stubborn. Lead the target in time, not in sight. What began as crew improvisation hardened into a systematic correction when ordnance officers paired battlefield reports with controlled trials. The result was a new set of ballistic corrections and a practical invention, the trailing offset firing table. Technical Manual TM9 to 294, 1943. On paper, the fix read like geometry. A shell fired from a 75mm M3 at 800 yards at a target moving laterally 10 km per hour required roughly a 0.6mm trailing offset to translate a frontal aim into an engine compartment intercept. A 76mm Sherman Firefly round at 1,200 yards needed about 0.8mm under similar motion. These numbers were not guesses. They came from synchronized range towers, high-speed photography, and chronographed powder lots provided by Lake City Arsenal. Ballistic Trials Report, Detroit Arsenal, October 1944. Engineers converted math to metal. Lieutenant Colonel Harold M. Pierce at Aberdeen and civilian site designer Walter J. Keane at Detroit Arsenal sketched new drum graduations and reticle markings. Machinists at Rock Island recut elevation drums, and toolmakers at Vickers and Colt produced shim sets to correct bore axis alignment. The work of Walter Keane's drawing board and the grinder at Rock Island turned field scribbles into parts that could be issued by depot clerks. Rock Island Ordnance Log, November 1944. Armor schematics explained why trailing worked. A Panzer IV ORSF. G carried frontal plates near 80mm while the engine deck and rear hull dropped to 30 to 40mm. Propulsive and cooling gear sat exposed beneath thin sheet metal, vulnerable to oblique impacts that struck the engine block or radiator. A small temporal lead converted a glancing frontal strike into a disabling rear engine hit. Captured German technical manuals and workshop reports confirmed the pattern. Captured German Technical Manual, 1943. The decisive proving ground came in the Bocage on July 25, 1944, near St. Miraglisse, when Task Force Raven, a composite commanded by Colonel James H. Dalton and including Company C of the 71st Tank Battalion, engaged a dug-in Kampfgruppe in sunken lanes. 3rd Armored Division Situation Report, July 25, 1944. The hedgerows shortened ranges and produced acute lateral motion as German armor skated along lane edges, perfect conditions to test trailing offsets in combat. Sergeant Alvin J. Mercer, a gunner with Company C, called lateral speed, range, and a 0.5 to 0.7mm trailing offset while his loader timed the charge. Mechanics had shimmed the bore after noon maintenance checks to ensure the axis was true. 71st Tank Battalion Log, July 1944. The first sequence immobilized 3 Panzer IVs, engines ruptured, radiators pierced, final drives locked, turrets intact but the vehicles dead on their axles. The battalion log recorded stunned enemy reports noting engine hit though the frontal plate shows nothing. 71st Tank Battalion After Action, July 1944. Statistical sheets from the engagement were stark. Of 22 enemy tanks contacted, 15 were immobilized and 9 destroyed outright. Attackers suffered 5 killed and 12 wounded. The kill and immobilization ratios correlated with units that had adopted trailing tables and calibrated sights rather than with random chance. Ordnance analysts cross-checked photographic evidence and found consistent rear compartment damage patterns. After-action statistical annex, 3rd Armored Division, July 1944. German signals intercepted that weak captured confusion and panic. We are hit in places that cannot be. engines burning though the front is untouched, composite translation. Intercepted signal log, German Army Group, July 1944, composite. Wehrmacht workshop notes added a grim footnote. An uptick in final drive failures and radiator ruptures that did not match previous combat damage models, forcing units to cannibalize spares in field workshops. Wehrmacht Werkstattbericht, July 1944. Scaling the change exposed logistical knots. Implementing trailing offsets required issuing new sight drums, recalibrating optics, and retraining crews across divisions. Production lines at Rock Island, adjustments at Vickers, and extra shim kits from Detroit were requisitioned and rushed to ETO depots. ETO Ordnance Logistics Directive, September 1944. Training centers at Fort Knox and Bovington appended live-fire modules on mill reading and predictive aiming. Instructors like Major Frank L. Donnelly wrote drills now standard in Armored School curricula. Armored School Bulletin, October 1944. The human and mechanical interplay mattered. Field maintenance cycles tightened. Bore wear was logged daily, chronographs measured propellant variance, and crews were taught to record temperature, humidity, and barometric pressure, small environmental factors that nudged muzzle velocity and altered required offset. Ordnance NCOs became translators, turning laboratory mills into actionable calls in the heat of battle. Field Ordnance Bulletin, November 1944. Engineers and factory hands took public credit only rarely. Their toil showed instead in manuals, parts, and lives saved. The Detroit foundries that cast site housings, the Aberdeen technicians who ran angled plate trials, and the depot clerks who matched parts to serial numbers quietly multiplied combat effectiveness. In their margins and on their drafting boards they rewrote engagement calculus. Speed of motion, percent of lateral velocity, and time of flight became the new axes of armor warfare. Aberdeen Proving Ground Test Notes, 1944. Across repair bays and drafting rooms, machinists and ordnance clerks worked double shifts, their measurements and trial scribbles moving from pad to front line and changing lives in a single campaign season daily. Bureau of Ordnance Correspondence, December 1944. By winter, the tactical change rippled across theaters. Immobilization shifted strategic calculations. Intact turrets with burned engines meant tanks could be interrogated and parts salvaged. The Wehrmacht found its operational radius shortened as mobility losses accumulated. Commanders who adopted predictive aiming bought ground and time. Those who did not watch armored opponents escape with only superficial wounds. U.S. Strategic Assessment, December 1944. The lesson was precise and even a little cruel. Superiority could arrive as an insight into motion, not simply as heavier steel or bigger guns. The trailing offset tables, the recut drums, and the boring room shims turned gunners into partial mathematicians and ordnance into a living discipline. The next section will trace the psychological aftermath, the engineers' names archived in orphan memos, and how this small correction bent campaigns. Bureau of Ordnance Correspondence, December 1944. The winter after the Bocage felt less like a pause than a reckoning. Armored columns that once prowled with confidence found their operational maps littered with dead iron. Turrets still polished, radios intact, but huddled on rims of roads with engines blackened and final drives fused. Intelligence officers compiled a new tally. Not only tanks lost, but how many were rendered immobile and later recovered. The numbers reframed campaign math. U.S. After action, December 1944. The psychological cost to the Wehrmacht surfaced in interrogation rooms and captured diaries. Panzer crews wrote of a new vulnerability. Our tanks stop like they have been betrayed from within. Composite translation. Command reports described a morale slide when commanders could no longer rely on mobility as escape. A disabled tank in a hedgerow allowed infantry to close and engineers to scavenge, each recovered engine feeding another Allied vehicle. Captured German unit memo, August 1944. Across American depots the tone was different. Sober pride. Quartermasters saw fewer full replacements needed when immobilizations, rather than outright destructions, dominated enemy losses because salvage returned usable parts. Depot clerks at Cherbourg logged engines and transmissions shipped home. Mechanics at Remagen rebuilt turrets, and ordnance officers wrote that sustainment became as much about recovery as production. ETO Ordnance Logistics Report, January 1945. The unsung technicians were linchpins. Field artisans, welders, turners, sight fitters, kept Shermans firing with consistent bore alignment, replaced worn rifling sleeves, and measured muzzle velocities with hand-cranked chronographs so crews could apply the right offset. Master Technician Raymond E. Halsey's neat notes, checked bore wear, 0.012 inch, advised plus 0.2 mil at 900 yards. Littered ordnance files. Their signatures are small in archives but enormous in consequence. Field Ordnance Bulletin, November 1944. Training doctrine absorbed the lesson. Armored schools added predictive aim modules, gunnery tables appended trailing offset charts, and instructors, many combat veterans, taught how to convert lateral speed into mil adjustments under stress. The change was not merely technical. Crews learned to see time as vector and motion as the true target. Armored School Curriculum, March 1945. At the strategic level, commanders reassessed attrition models. Immobilization rates affected operational tempo. Slower enemy columns meant fewer breakthroughs. Bridges that once allowed withdrawal now funneled trapped vehicles into kill zones. Staff officers began to model logistics with recovery rates as a variable, rewriting plans that had assumed quick retreats. U.S. Strategic Assessment, 1946. Field medicine and POW handling shifted. Intact but immobilized turrets meant crews surrendered whole. Medics treated shock and frostbite more than blast trauma. Interrogators gained living witnesses who described tactics and factory numbers. Each captured crew yielded human intelligence and technical plates that corroborated engineers' field findings. POW interrogation reports, 1944. Industry changed in response. Factories tracked interchangeability and repairability under combat conditions. Detroit foundries and Rock Island shops thought in loops: produce, test, field report, revise. Engineers like Walter Keane and Lieutenant Colonel Harold M. Pierce saw drawings annotated with field scribbles, add .015 shim, change drum gradation, until design officers resembled extended conversations with frontline crews. Rock Island Ordnance Log, 1944. That conversation shaped post-war doctrine. Cold War planners studied Normandy reports with keen interest. NATO tank studies emphasized not only frontal armor but engine compartment hardening, redundancy in cooling systems, and easier field access for repairs, lessons drawn from rear compartment vulnerability exploited by predictive aiming. NATO Armored Study, 1952. Beyond tanks, the conceptual lesson migrated into air and naval gunnery. Aim where a target will be, not where it is. Anti-aircraft crews refined predictive lead tables for faster aircraft. Naval fire control engineers folded time-of-flight calculations into automatic trackers. The wartime marriage of field observation and rapid engineering iteration foreshadowed sensor-driven warfare. Bureau of Ordnance Correspondence, 1946. Yet the lesson carried a human edge. Crew improvisation, the daring of a gunner to aim just off the sight line, the patience of a loader to hold around until predicted alignment, required discipline under fire. After-action reports credited both sight revision and gunner judgment as causes of improved immobilization rates. 71st Tank Battalion After Action, July 1944. Post-war memoirs made room for awkward pride. Engineers remembered drafts and shop floor debates. Gunners remembered nights calibrating in moonlight to the hum of distant artillery. Veterans' reunions featured arguments over mil values and bore tolerance, technical conversations that doubled as memory rituals. These small disputes told a larger story. Warfare had become a contest of measurement and imagination as much as of courage. Veterans' Memoirs Collection, 1961. Ethically, the tactic targeted machines, not men, but its consequence was to make mobility brittle. A single well-placed offset could turn an offensive into slow attrition of recovered hardware and exhausted crews. Strategically, timelines lengthened, supply-demand shifted, and political timetables for offensives bent under logistical realities. U.S. Strategic Assessment, 1946. In the end, legacy was granular. A recut elevation drum saved a platoon. A shim in a sight housing allowed a gunner to trust a decimal. A welder's late-night grind returned a transmission to service. Those margins of metal and moments of courage bent campaigns and taught militaries that precision of prediction can be as lethal as raw force. Bureau of Ordnance Correspondence, 1946. The technical thread ran through small civilian shops as well as ordnance yards. Night shift toolmakers at Detroit's Packard plant, lathe hands at Bethlehem Steel, and optical technicians at Bosch and Lomb adjusted tolerances frontline crews could rely on. Their union of craft and calculation turned anecdote into doctrine. Maintenance cycles tightened. Field units logged bore wear, propellant lot variances, and ambient pressure in appendices to reports, feeding a feedback loop that kept sites and tables honest. Industrial Production Notes, 1945. That iterative bond between Smith and gunner changed the calculus of war. Machines are measured by their movement, and movement can be cheated. An archive engineer is recorded saying in a post-war notes file, composite. Ordnance Archive Notes, 1946. The truth from hedgerows, workshops, and interrogation rooms carried forward into doctrine. In modern war, connection and timing can outweigh sheer firepower.